No, I'm not here to bully you. I'm just here to smile at you.
So you should bully me if you think you should.
Trust me.
Why is homework 4 so long?
Pardon me?
Why is homework 4 so long?
What do you mean by long?
It's like, looks very challenging.
It's actually not. So I had all of my TAs try it over the weekend, and I gave it to them on Saturday. And Danish submitted his A grade last night at 2 in the morning or something.
How long do you work on it?
So from when I released it to when he submitted it, right? So if you know what you're doing, it's not very long.
Okay.
I'm giving you 3 weeks to figure out what the heck it is, to know what the heck it is you're doing.
You did it last week.
And I mean, all of these homeworks are super long for a very simple reason. I give you 6 weeks, 2 weeks, 3 weeks, 4 weeks, 6 weeks, 16 weeks, 52 weeks, and well, you spend 51 weeks worrying about it and 1 week working on it. In your mind, you've been working 52 weeks. In practice, you've been working 3 nights, right? And panicking. So if you actually push the panicking up front to the first 3 days of those 52 weeks, you have the rest of the year free, and it feels really short. It's all about attitude, right? So I did a little informal survey of a few people about how the course went, and everybody thought it was too much work until I actually dug around and found out where it is they were spending their time. They were spending all of their time worrying and very little time working. That's not a very, very effective use of your time, is it? So anyway, this is the last of the series of lectures on Hopfield nets and Boltzmann machines. Let me pick up a quick recap since it's been a few days. This was how we defined a Hopfield network. This was our first introduction to networks which talk back to themselves on a single input. Well, there's a difference between, actually this is not the first time you've seen this. We've seen networks which speak back to themselves earlier. When was that? Recurrent neural networks. If I gave you a recurrent neural network which had only one input and then proceeded to operate on it, and all it did was kept updating its hidden representations, you're going to have something very similar to this, right? But then let's talk back about the Hopfield network itself. There was something interesting about the Hopfield networks. Now this was how we defined the network. You have a bunch of units. Every unit is connected to every other unit. So every unit outputs to everything else, every unit receives from everything else. We're considering the special case where the weights are symmetric, but this is not a requirement. It's just a matter of convenience because it's easier. It doesn't fundamentally change the behavior of the system to any great extent, but this is just easier to interpret. Come to the front rows, please. I don't have a mic. So here's how each unit was. Each unit saw a weighted combination of the outputs of the other units, and if this weighted combination exceeded a threshold, it fired, otherwise it didn't, right? So how long? And so what would happen is that each unit would try to align itself with its local field, where the field was this affine combination of the outputs of the other units, and it would flip. Sometimes it would flip, but if it flipped, this changed the field of the other units. They would flip in response, which might cause the first unit to go right back and flip, and so on. How long would it evolve? How long would this evolution continue? We saw how we can actually quantify this. We can define something called the energy of the network, which is given by this formula over here, which is a weighted combination over all pairs of neurons of the product of the outputs of the neurons, or the negative of this one. And you might have an extra bias term. I can write this energy term as a quadratic formula using vector notation. If I represent the outputs of all of these neurons as ones, as a single vector y, then and the weights as a matrix W, then the energy is minus half y transpose Wy. We've seen this, right? And the network will continue to evolve, and what we were guaranteed was this energy term would decrease any time a bit flipped. And so the network would continue to evolve until the energy hit a local minimum. Now, although this is a quadratic and has a global minimum in many situations, it has a global minimum value and might even have a global minimum configuration. That's only when it comes to when you factor in the fact that these y's themselves lie on the corners of a hypercube, there can be many local minima and so where it converges is going to depend on where it starts from. We saw this, right? So here's how the network would behave. You set the network with some initial pattern, then you iterate through all of the neurons, and at each neuron you just look at the current field at the neuron and try to align the neuron itself to its field, and then keep looping through the neurons, and you continue this until this energy term doesn't change anymore, at which point here you have arrived at a local minimum. And so the evolution, if you plotted the energy contour against the state, of course the figure is not going to look anything like this because the states are multidimensional binary vectors, but this is just for illustrative purposes. Then the network would start at some configuration, and it would roll down the energy contour till it hit a minimum, and then it would local minimum, and then it would stay there. So this gave us something called a content-addressable memory. Each of these local minima was a pattern that the network likes to evolve to. So each of these local minima can be thought of as a memory that the network remembers. And if you give it a corrupt version of this memory, something that's damaged by adding noise, erasing some bits, whatever, then it's going to evolve and recall the entire memory starting from this corrupt memory. So it's a content-addressable memory, also called an associative memory. All of this we've seen. And so here are some examples. If you trained a network to remember, say, these two patterns, if you initialize the network with this guy, it would evolve until you got this one. If you initialized it with this guy, it would evolve until you got this one. In fact, these two are actual examples that I got from this university in Australia. Now, this over here is the completion of a noisy pattern. You initialize the network with the noisy pattern, you let it evolve, it completes the noisy pattern. This one is pattern completion. So this one is actually denoising more than pattern completion. This is pattern completion. I give it a partial pattern, it remembers the rest of the memory. Ideally, you want to design the network so that I don't have to give it half the pattern for it to recall all of it. You should be able to give just enough of a pattern. Even if you give it much lesser, it should be able to recall this. But to get this done, you would have to design the network to remember things in a proper way, which led us to the problem of training a Hopfield network to memorize target patterns. So you will have to train it to remember specific target patterns. In the two previous examples, you would have to train it to remember the Chip and Dale or the Looney Tunes picture. Now, can we use backpropagation to train the network? Why do you think so?
As long as you can define the loss function appropriately.
But it's a loopy network, right? Backpropagation was designed for feed-forward networks. So how would you use backpropagation over here?
I think you can define a loss function on the energy.
Yes, but then again, backpropagation is you're going to keep looping back, right? So you have to, backpropagation assumes that you have a directed graph for the network, yes.
Would it really matter if you were to pick any of those random nodes and treat that as your final destination and then trace along one of the random paths that connects everything?
Yeah, but you're still going to keep looping back. So what you would have to do is to actually unroll the network. This is exactly what we do in a recurrent network, right? So if I have all of my neurons, then this is t equals 0. You set it at some value, then you get a full set of connections going forward. And so the evolution of the network really is a time evolution. I can unroll the evolution of the network just like I do in a recurrent network, right? And then eventually at some point, depending on now what really, the problem really is this business of how long must you unroll it. But you can keep unrolling it until the pattern stops changing, at which point you can give it your target values out here, compute a loss, and work your way backwards and update the network. Of course, it's kind of conceptually possible to do this. In practice, this is going to be a bit of a pain because, where do you start? If I start off with some initial value, what is the correct target value to give it at the output? How long do I let it evolve? You get all of these crazy questions, right? But you understand what I'm talking about over here. So which is why we don't actually use backpropagation to train these networks. Instead, we do something else. We design the matrix W such that the energy of the target patterns is minimized so that they are in energy wells, and other targeted potentially parasitic patterns have their energy maximized so that they don't become parasitic. So basically, if I gave you this, if I have the energy contour for the network for different states, I want to design my network such that the energy for my target patterns is as low as possible, and the energy for every other pattern is very high. So you can define a loss function of this kind, which is, now this is not backpropagation, right? But you're still doing gradient descent. This is the total energy of all of my target patterns. This is the total energy of every other pattern that the network could possibly represent. And you're trying to minimize the energy of the target patterns and maximize the total energy of all the non-target patterns. So you can define an objective of this kind. And because the energy of for any pattern is simply given by this quadratic, this minimization can be done using gradient descent. So what is the derivative of this guy? Now we know that the derivative of minus y transpose wy with respect to w is simply yy transpose. This we've already said. This we've known for many months at this point. So the derivative of this term here is going to be the sum over all the target patterns of the outer product of the patterns. The derivative of this term over here is going to be the sum over all of the parasitic patterns of the outer product of these patterns. And so this whole thing is going to give you the simple gradient descent. So what you would be doing is minimizing the energy here, raising the energy everywhere else to train the weights matrix, except that if you did so, this summation requires a summation over an exponential number of combinations, and we didn't want to do this. So we changed that and said it's sufficient for us in each setting of the weights matrix to try to simply raise up the valleys. The number of valleys is going to be much smaller than the exponential number of states. So if you just found the valleys and raised them, and then you push down your target patterns, because you're always at each iteration you're pulling up the valleys, eventually your target patterns are going to be lower than have lower energy than any other pattern, and they become the memorized patterns. This was the theory behind this approach. So we would focus on minimizing the number of parasites that can prevent the net from remembering the target patterns. So the overall approach was you would try to minimize the energy over here, but then you would initialize the network from these target patterns and let it evolve to the closest valley and raise that valley. Because we were kind of focusing at this point on not raising the energy everywhere, but making sure that our memories are memorable. If you start in the vicinity of the memories, you do end up with the target patterns. So all of this we've seen so far in the class, right? None of this is new. Any questions? We're going to it gets more complicated pretty quickly, although much of this class is a repeat. So now the final bit that we saw was that for more efficient training, there was no need for us to start from here and roll all the way to the valley. It was enough to say that for each target pattern, I'm going to pull up the vicinity of the pattern, just the neighborhood of the pattern. And so we said, we just want to make the target memories valleys and everything around it to be higher than have higher energy than this and than the target pattern. And so the way we did it was we would try to minimize the energy of these target patterns, but from each of these target patterns we would let the network evolve 2 or 4 steps till it got to something which was somewhat close by but had lower energy, and then raise the energy of those patterns, and you keep repeating this. So the overall algorithm is you're going to be sampling your target patterns, and now observe that by sampling your target patterns you're also naturally accounting for the fact that some patterns may be more important than others, which means that you can think of these target patterns as having some patterns are more important to remember than other patterns, and the way you would do it is to present the more important patterns more frequently during the sampling and present the less important patterns less frequently during the sampling. And so you would sample the target pattern, and then you would initialize the network at that pattern and let it evolve 2 or 4 steps till it arrives at some down valley position from that pattern. And then you'd update the weights using this update rule, which is you're reducing the energy of the target pattern and you're increasing the energy of the down valley pattern that you arrived at from the target pattern, right? Yes.
I'm thinking about pulling the neighbor's position only will create us additional values in this in the whole structure. So which means we have additional parasite points here.
So where we have chosen to focus on the targets, which means that we're ignoring the fact that if you're far enough away from the targets, you might have parasites. That's okay by you, simply because we have to deal with the fact that there are an exponential number of these other patterns, and there's no way you're going to actually be able to explore all of them and raise them up. So you have to pick your battles, and this is how we actually deal with it, right? So, and yet, after all of this, getting back to your point, and why we can try to get away with this, is we found that the recall pattern was not perfect. So here, if I start with this degraded noisy pattern, what I got was this guy, which is not really Bugs Bunny, right? It's Bugs Bunny with speckle noise. So why do I have this? And this was where we kind of almost ended off. We discussed several more points after this, but we'll recap all of them. The point was that if you looked at the energy contour, you had all of these parasitic memories, some of them very close to this guy, which were not memories that you really wanted, but nevertheless had local energy dips that the network could fall into. So in this case, what do you think has happened over here? What has happened is it looks like Bugs Bunny, right? Except it's Bugs Bunny with noise. So what has really happened is something like this. You have the state, again, keep in mind that the state is not a continuum. This is just an illustration. This is ideally, this should have been Bugs Bunny. But what you've got is something like this. Which is pretty close to Bugs Bunny, but some of the bits are flipped. And that's where the network is sort of descended into, right? So, and now we have speckle noise. Now I've given you this problem. Can you suggest a way to actually make sure that when you're actually falling into this guy, somehow you can jump back here? How would you do it? You can add a little bit of noise, right? But adding noise is maybe going to push it back up, and it just comes rolling right back down. So what exactly do you want to do? You want to say that if I fall into a local energy pattern, local minimum, you want to consider the fact that that local minimum might actually not be the one that you want, which means that you want to give your network a chance to actually continue to evolve, and even though the current state is a local energy minimum. And the way you must do it is that whatever mechanism you choose should be such that if the local energy minimum is a small dip of this kind, it will go out. But if the energy minimum that you have is large, then the mechanism that you choose for letting the network continue to evolve after it gets to this local minimum should eventually still bring it back to this guy. So for big valleys, this should not hurt it. For small valleys, it should give it a chance to escape, right? Now, the way we'll do it is to convert the network to a stochastic machine. So here's how we do it. We're going to treat the Hopfield network as a probability distribution. And now this was what the energy was for the network. Our original objective was to try to minimize the energy of the network. If I take e raised to minus energy as representing my probability the probability of a particular state, then not appropriately normalized, which means that I must also divide by the sum of the e raised to minus energy over all states, then this is minimizing this guy is the equivalent of maximizing this guy, right? Which is to say, I want to find the states with the highest probability. Now, this hasn't really changed anything. If minimizing the energy is the same as maximizing the probability, what have I changed? What has happened is that in the process, you have converted this to a stochastic machine. And how does converting this to a stochastic machine help me? Now consider these two configurations. They are the same except for this one bit. Here this is the state, the bit is +1. Here the bit is -1. Now what is the probability of this configuration? That's going to be the probability of all of the remaining bits times the probability of this one bit given the remaining bits. The probability of this configuration again is the probability of the remaining bits times the probability of this one bit given the remaining bits. Now in these two cases, the remaining bits are all identical. The only thing that changed is this bit that we are highlighting. In one case, it's going to be the probability of this bit taking the value 1 given the rest of the bits. In the other case, this is going to be the probability of this bit taking the value -1 given the rest of the bits, right? And now if I take the log of these two probabilities, the log probability is going to be the log of this first term plus the log of this second term. So if I take log of PS minus log of PS prime, this guy goes away because their logs simply cancel out. And so you're going to be left with the probability of the first term, the probability of this, the log of the probability of this guy taking the value 1 given all the rest of the bits, minus the log of the probability of this guy taking the value -1 given the rest of the bits, right? And we know, of course, that anytime I write log A minus log B, equals log of A over B, right? In this particular case, we've got B equals 1 minus A, so this is going to be log of A over 1 minus A, right? This is basically what we've got over here. And so we have that the log of the probability of this state, where S is where the bit is 1, minus the log of the probability of this state, which is the same as this guy except that this one bit has taken the value -1, is simply log of the probability of this state taking the value 1, this bit taking the value 1 given the rest of the bits, divided by 1 minus that same value. So this is just very simple arithmetic. I haven't actually done anything particularly complicated, right? Although there are too many equations on the board, but this is something you're going to have to get used to. Questions? No. So why am I going through all of this? Now, if you look at the log of the probability for any given state, the way we defined it, this is just the normalizing constant, you can ignore it, but it's going to be the log probability of a state was minus of the energy, right? That's how we defined it, because the probability of the state was e raised to minus energy, so proportional to. So now if you look at this, the energy at this state, it's going to be it is -12 of, so the energy at any state we know is -12 of summation Wij Si Sj, summed over all of the states, correct? So this is summed over all I and j. which I can write as minus half of summation over I W. Well, instead of getting into too ugly notation, because I'll have to introduce a third index, let's just look at the picture, and the picture will tell you what's happening. So when I write this guy here, I can write the energy in terms of, separate it out in terms of two components. The first component is the contribution of the energy from all of the terms which include only these 4 bits. And so that is going to be common for both of these patterns, because they don't include the target bit itself, right? And then there's the remaining, which is the interaction of this bit with each of the remaining guys. And the interaction of that bit is simply going to be whatever, so I can write this as minus half, and this is not the ith bit, plus what is the interaction of, say, what is the energy of this guy? Here the value of the bit is 1. That's going to be 1 times Wij times 1 times Sj plus summation j, this is going to be 1 times Bi. Correct? In the other case, it's going to be, for the second term, it's going to be minus half. The not I bit is still the same, plus summation j Wij times minus 1 times Sj plus minus 1 times Bi. That's the difference in the energy between these two guys, right? Which is basically what I have written over here. So I just, instead of explicitly multiplying by 1 or minus 1, I've just put the sign in. So the energy for this state is going to be, this is minus half term outside. This is everything that doesn't involve the current bit itself. This is simply the weighted product of all of the remaining bits plus the bias of the current bit. For the state where the bit takes the value minus 1, it's going to be minus of the weighted product of all of the remaining bits minus the current bias, right? So if I take now again, since the log of the probability is the negative of this energy, if I take the difference between the log of the probability of the state S and the log of the probability of the state S prime, that's simply going to be this term minus this guy. That turns out, after all that ugly looking arithmetic, is that it's simply going to be the weighted sum of the values of the remaining bits plus the bias, right? And this is where things get nice and simple, because at this point I have log of PS over 1 minus PS. This is PS equals 1 given j not equal to I, right? Si equals 1, and this is Si equals 1 given Sj not equal to I, equals summation j Wj Sj plus Bi. This is basically what we've got. And if I expand this out, I can write this as P of Si equals 1 given Sj not equal to I divided by 1 minus P of Si equals 1 given Sj not equal to I is e raised to summation j Wj Sj plus Bi. I just took an exponent, correct? I can flip this around and I can say 1 minus P divided by P equals e raised to minus summation Wj Sj plus Bi. I haven't actually written the P term very carefully. And what is the result of all of that? If you just work this out, it turns out that the probability that the current bit takes the value 1 given all of the remaining bits is just your standard logistic function. This is your sigmoid, right? And so it's very beautiful. You go through all of this ugly looking arithmetic, and it turns out that we end up with something that's very familiar. It looks like a neuron with a sigmoidal activation, right? But now ours is a probabilistic machine. So what happens? We're going to, if you're trying to redefine Hopfield networks as a stochastic system now, each neuron is a stochastic unit where the probability that the neuron is going to take a value 1 is going to be given by this logistic function, right? And I'm going to now switch. So far we were assuming that the neurons take the value either +1 or -1. I'm going to switch my notation a bit. I'm going to say they're going to take the value either 0 or 1 just to stay consistent with the literature, but nothing really changes. The logic remains the same. So this is what, so first, what does this whole thing mean? What has happened is the Hopfield network, we've converted the entire Hopfield network as a probability distribution over binary sequences, where the probability of any binary sequence is now a Boltzmann distribution, but the conditional distribution of the individual bits given the remaining bits is a logistic function. That's your sigmoid, right? How does this help me? Here's what I will do. I'm going to initialize the neurons. Remember, I'm still sort of interested in all of this ugly arithmetic wasn't trying to help me get out of this guy. Yeah? So here's what I will do. I'm going to initialize the neurons as before, but during my evolution, instead of doing the deterministic evolution that I did in the past, what I will do is that for each neuron, I'm not going to just flip it if it's misaligned with the current field. Instead, at each neuron, I'm going to compute this logistic function. And that's going to give me a value between 0 and 1. Then I flip a coin with that value as the probability of heads. And if the coin takes the value 1, I'm going to set the neuron to be 1. If the coin takes the value 0, I'm going to set the value to be 0. And then if you think very carefully about it, what you will find is that if the magnitude of z is very high, then what does this look like? This just becomes either a 1 or a 0, right? So when the magnitude of z is, say, let's say z is a very large negative value, and the current value is and the current value is also negative, right? Now, what will happen is the probability that you're going to switch to, if z is a very large negative value, this term becomes 0 because e raised to minus z is infinity, right? So if you're currently a minus 1, the probability that it's going to take a value 1 basically becomes 0, right? If z is a very large positive value, then the probability that it takes a value 1 becomes 1. So basically this is just, I've just taken my threshold function, I've smoothed it out. That's all I have done, right? But then over here, even though I've arrived at a local valley, right? What does a very large negative value or a very large positive value really mean? A very large negative value means that the valley is really deep, the energy is really deep, right? Energy value is really deep. So, or the energy is really high. So if I still have a small probability of flipping the bit, and when I flip the bit, I'm actually going to sort of get out of a local valley, which lets me evolve into a deeper valley nearby. So I introduced this probabilistic mechanism which allowed you to jump out of these noisy positions to get to something better. But this is still not enough, because I can come out of here, this allows me to jump out of this guy, but then I come here and I'm still going to keep bouncing around, right? Because I always have a probability of flipping. I don't want to do that. Eventually I want it to stop in the valley. So I'm going to add one more little thing. I'm going to introduce a temperature term. Instead of just taking the local field, I'm going to take 1 over T times the local field. And all of this is motivated by statistical mechanics. The standard Boltzmann distribution does have a temperature term to it, right? So now, if T were 1, you're going to get the standard, the mechanism that we just saw. If T is not 1, what happens? Again, the probability that the current bit is going to take the value 1 is going to be a sigmoid over this z. The probability that it will take a value 0 is 1 minus the sigmoid. Instead of deterministically responding to the local field, each neuron responds probabilistically. So this is much more in accord with thermodynamic models, and the evolution of the network is more likely to escape spurious minima. But then here's what happens. First, the summation term quantifies the energy difference obtained by flipping the current unit, right? So why does this actually help you escape this guy? If you look at this one, this energy difference over here is really very small. So it has a reasonably high probability of getting out of that valley, even though it's a local valley. On the other hand, if that same thing had been something like this, the energy difference from flipping one bit would have been very large. It's not going to flip, right? It's only going to flip those bits where flipping the bit doesn't cause a tremendous change in energy, which is a nice way of trying to get out of these little dips in your energy contour, number one. Now, number two, if the difference is not large, right, the probability of flipping a bit begins to approach 0.5 because this whole term becomes 0. If the energy of difference from flipping one bit is not large, the whole term becomes, so the probability of flipping becomes 0. This is all very fine. But the most important bit is the temperature T, right? If the temperature is 1, then this is the standard Boltzmann machine that we just saw, which has stochastic behavior. What happens when the temperature is 0? When the temperature is 0, basically I'm scaling this energy out. So so basically as I keep increasing the temperature, remember this is how your sigmoid looks, right? As I keep increasing the temperature, I'm making the sigmoid squishier and squishier and squishier. When the temperature is exactly 0, this ends up becoming a step function. So when the temperature goes all the way down to 0, eventually it becomes a deterministic Hopfield network. It's no longer the stochastic Boltzmann machine, right? So now remember how the Hopfield network evolved. You're going at each point, you would initialize the network with some initial pattern. You're going to iterate through the networks. But now if I replace the Hopfield network by this Boltzmann machine, for each of the neurons, you're going to compute the probability for each bit that it takes the value 1. And you're going to choose the value for the bit by drawing from this probability distribution, basically by flipping a coin with that P, with the probability of heads being that P. So when do you stop? So assume that you don't have the temperature parameter, right? This is what you actually use. If I don't have the temperature parameter, then it's going to go down, but even over here it's going to keep bouncing around. And so since it's going to keep bouncing around, there's no way of saying what is the memory it actually recalled, right? But what is the behavior you'd actually expect it to show you? The behavior you'd expect it to show is that you're going to keep bouncing. It's going to keep bouncing back and forth, of course. It's going to keep bouncing back and forth. And then eventually maybe it comes out of this, keeps bouncing back and forth. But when it comes here, it's going to keep bouncing back and forth over here, right? So if it's bouncing back and forth at that point, how do I know what is the memory that I really want? I let the network evolve for a very long time, and I keep track of the states it goes through over many steps after it has evolved for a very long time. And then I just find out the average over many steps. And for each bit, if that average is positive, I set that value to be 1, otherwise I set it to 0. So basically if a bit is 1 more frequently than it is 0, then it likes that bit to be 1, otherwise it likes it to be 0, yeah.
I still don't understand why we made the whole system stochastic. Like, why couldn't we just, like, I don't know, increase the learning rate or add, like, momentum to get out of the local minimum?
So again, the point is, there is no momentum, right? So the gradient descent was for learning. This is for recalling, right? For recalling, remember what we did. I'm not speaking of learning. Again, this is all about running the network. How do I actually find? So we briefly mentioned the behavior of weights, but we haven't actually gone back to the problem of learning weights. How did I convert this noisy version of Bugs Bunny to a cleaned version of Bugs Bunny? That is the problem, right? Just to be very clear. And so that's why we're introducing this entire mechanism where we let it get rid of speckle, right? So And this, hopefully, yes, Michael.
I'm thinking instead of keep tracking of all the a series of bouncing points, what about we pick one of the bouncing point and do the deterministic evolution so that we could get that exact.
So here's what we do. Now that I introduce the T, here's what I can do. I can start off with a high energy, high temperature. When I have a high temperature, it has a much greater likelihood of accepting increases in energy. But over time, I keep decreasing the temperature down to 0. Eventually, the temperature is going to become 0. And when it's at 0, it's going to become deterministic. But then what happens is that by bouncing around, you expect it, and you can actually mathematically prove that if this T goes down to 0 slowly enough, it's going to escape all local minima and in fact going to find the global minimum. If the T doesn't go down infinitesimally slowly, it's going to find a local minimum, but it's going to find a nice deep local minimum. And eventually, because T becomes small enough, the behavior becomes deterministic, and as Michael mentions, that's actually now going to stop at the correct location, right? So this is the process of annealing. You start off at a high temperature and cool the whole thing down, right? Questions? Yeah. So noisy pattern completion, initialize the entire network and let it evolve. For pattern completion, you fix the scene bits. You don't change the scene bits. So there's a difference between the two behaviors. In the noisy pattern completion, I allowed every bit to change. But when I'm performing pattern completion, I'm fixing the upper half of the picture, which I know is Bugs Bunny. And the only bits that I allow to change are the portions of the picture which I don't know. And those will evolve eventually into Bugs Bunny, right? Or Chip and Dale, in my case, right? The example. So you see the difference between the two problems, right? So yeah, I said I let it evolve. I just keep letting it evolve. When do I stop, right? When do I stop? Well, the conditional probability of each neuron has been given by a conditional distribution, but what is the overall probability of the entire set of neurons? What is the probability that it will take any particular configuration y? This we know, right? This is simply the Boltzmann probability. We know what it is. And so I let it converge until this probability converges. So it's arrived at a maximum probability configuration. So the outcome of all of this is that although I started all of this as a mechanism for trying to recall memories, what we did was to convert the Hopfield network into a distribution. I converted it to a Boltzmann distribution. And in fact, where the conditional distribution of the individual bits is a logistic, but the overall probability is a Boltzmann distribution, the entire probability model can now be thought of as a generative model. If I start the network and let it evolve, the probability that you're eventually, after a long time, when it's actually hits a steady state, the probability that you're going to find it in any given state is given by this formula. It's a generative model. It's able to generate state sequence, state configurations, where the probability of generating any particular configuration is given by the Boltzmann probability, right? It's a nice generative model, and you can use this to model different probability distributions. So we started off with the Hopfield network. We ended up with a generative model, which is very beautiful. And now, how do you train the network now? We've just converted this to a stochastic model, right? So, but you still have to think about it in terms of, it's convenient to go back and keep thinking about it in terms of the content-addressable memory. So you want to train it, which means training it means you're learning these weights. You must learn the weights to remember the target states and dislike other states where you don't want it to stop, right? So in other words, now more importantly, I've changed the notation from Y to S over here suddenly. Not all target states are equally important. So you wanted to assign more probability to target states that you like more, maybe slightly less probability to target states that you like less, and hopefully 0 probability to target states that you don't like at all. This is the steady state behavior that you're speaking of, not during the evolution to steady state, right? So But then what is the probability of any particular state? That's just given by this Boltzmann distribution, right? This guy, which I can expand it out into this form. This energy is simply the weighted combination of the product of pairs of units. Observe that the minus went away, right? So what I do is I want to actually train the network to assign a desired probability distribution to states. In other words, I can just ignore everything, right? Ignore this business of like and dislike. I can literally say, here is the probability distribution that I want. I want 0 probability for all of these states. I want non-zero probability for these other states which I think are useful memories. And some of them are more important, so I'm going to give them more higher probability. Some of them are less important, I'm going to give them lesser probability. So basically, you just wanted to model a probability distribution over states at this point, which means that what you would be doing is you would be giving it a set of training inputs, a bunch of patterns that it likes to remember, where patterns might be repeated, some patterns might be repeated, or you might actually have a notion of an importance for each pattern. So you assign higher probability to patterns you like more, lower probability to patterns that you don't like. Alternately, and you design the network such that the probabilities of the network being in one of these states at steady state follows the distribution that you have. You want to maximize the likelihood of the probability of the good states and minimize the likelihood of the probability of the states that you don't want. So this is the maximum likelihood. You want to maximize the likelihood of the states you wanted to store, right? These are the states you wanted to store. You want to maximize the likelihood of this probability of the states that you want to store, which leads us to very simple maximum likelihood training. So I can define the likelihood for any given state as just the log, or the log is as this term here. The log likelihood is going to be the log of this probability, right? And again, observe that suddenly the math has become a lot more complicated simply because you went from looking at a nice, very easy to interpret deterministic machine, the Hopfield network, where there was nothing particularly complicated. You're just looking at quadratics. And I threw Boltzmann machines at it, made the whole thing stochastic, converted it to a generative model, and now you're looking at some not very nice looking equations. Yeah.
So isn't this the conditional probability?
No, this is the probability of the entire. This is the probability of a full state. The conditional probability was the logistic, right? Right. So this one is just the probability of this is the e raised to the minus energy of the state, and the denominator is just the normalizing term, right? So now what happens when I take the log of it? The log of it is going to be the log of the numerator, which is simply this weighted combination of state pairs. The denominator is much uglier. It's summed over an exponential number of states, right? So when I sum it over an exponential number of states, the denominator is going to result in this term minus log of the sum over all possible states that the network can arrive at, okay, that the network can be in, of e raised to the weighted combination of state pairs for the state, right? And this is the log probability for one state. If I have n training instances where I have n states all stored in this, so this bold S represents a set of states that I want the network to actually represent, the distribution to maximize the likelihood of. And so this guy, I'm assuming over here when I say S belongs to cap bold S, that this includes preferred states with greater frequency, less preferred states with lesser frequency, and so on. That actually represents the distribution that you would like the network to store, or the importance that you assign to the different states, right? So this is simply the overall log likelihood is going to be simply the average over all of your training instances of the log of the probability of the individual states, which again I can expand out, and that's going to be the average. So observe that this ends up looking very, very, very familiar, okay? So what is this term over here? This is this guy is going to be the average or negative average of the energy of the states, right? Or the average of the negative of the energy of the states that you like. All that happened was that now you have the second term over here. So this guy literally looks like one of the things that we saw in your when you are training the Hopfield network. The second term is the one that's ugly. The second term, which they'll famously like to call the partition function, is the log of the sum over an exponential number of states of e raised to minus of the energy of the state, right? So if I want to do a maximum likelihood estimator, I have to maximize this guy, which means that I want to compute the derivative of this term, and now I'm going to be using not a gradient descent rule, I'm going to be using a gradient ascent rule, right? But then let's go back and look at what is this derivative of this guy. The derivative of this guy has two terms. The first is the derivative of this term itself, right? If I take the derivative of this first term with respect to some wij, then all the summation terms which don't include either wi or j go away. So all you're left with is the average over all of your training instances of the product of the states I and of the bits ith and jth bits. The second term is the derivative of this. This should be gradient ascent. Okay. Can somebody pose this on Piazza? That's got to be gradient ascent. Okay. Errata for today's slides. Okay. The second term is the derivative of this ugly guy, right? But it turns out the derivative of this ugly guy is not so ugly. It's actually very, very simple. It's kind of beautiful, and it turns out that we wasted a lot of time. And let me explain why we wasted a lot of time. So I have the derivative with respect to ij of log of summation over s prime e exponent of summation over ij wij si sj, right, which is going to be 1 over summation s prime exponent of summation ij wij si sj times the derivative with respect to wij of the summation of s prime over s prime exponent of summation ij wij si sj. I haven't done anything magical, right? Which I can write again as the summation can come out, s prime comes out, because the summation doesn't really matter. This is going to be 1 over summation, I'll use a different s double prime over here, exp of e of s double prime. So I save myself the trouble of writing all of that term minus. And what is the derivative of the exponent? That's going to be the exponent itself times the derivative of the term inside, correct? That's going to be the exponent of summation ij wij si sj times d over d wij of summation ij, right? So which I can write as, again, summation over s prime exponent of blah divided over summation s prime of exponent of blah times si sj. Now observe what happens. I'm sort of taking shortcuts. I just wrote that down. I just pulled the all I did was to say that this derivative just leaves you si sj, correct? The final derivative. And I just pulled the exponent right over the denominator. But this term, what is this term? That's just a probability, right? It's just going to be the probability of S prime. So the whole thing ended up being the summation over all of the states of the probability of the states times the product of the pair of bits for that state, right? So it looked so ugly, but at the end of the day, what did we get? The expected value of the product of the pair of states, pair of bits, over all states. Now once I realize that it's an expected value, something magical happens. I know I cannot compute the expected value anyway, because this still requires the summation over an exponential number of patterns. But then what do we know about computing expectations? You can compute expectations by sampling. So what I can do is I can, instead of computing this, I can randomly draw many samples from the Boltzmann distribution. Over all of the samples, I can compute the product of those pairs of bits, take the average, and this average is going to pretty much give me a pretty good guess for this guy. Yeah.
In this sampling, do we still have the preference over some specific state of the?
No, this is over all possible states, right? So this is just arbitrary, right? So you're letting you have the current set of parameters, the current weights. Remember, you're trying to compute the derivative, right? So here, if you go back to this equation over here, only the first term, the numerator term, had a preference. The numerator term was the average over the training instances. The denominator term was generic to everything else, right? So this, how exactly do you sample from a Boltzmann distribution? It turns out it's very easy. I can initialize the network randomly, just let it evolve. After it's evolved for a long time, I can take a bunch of snapshots, and each of these snapshots is going to give me a simulated sample, a drawn sample, right? I have to let it evolve long enough that I think it's now in steady state, and then I can begin sampling, taking snapshots, and those are my samples. And so the actual process now of computing this derivative can be changed, or the second term in the derivative can be thought of as taking the average of the product of pairs of bits when I run the network in simulation mode. I just set up the network with the current set of weights, let it evolve, and then take a bunch of snapshots, right? And so what does the whole thing become? The whole thing becomes this guy. This first term was the average over your training instances of the number of the product of pairs of bits. The second term became the average over all of the evolved samples of the products of pairs of bits. And then you're just doing gradient ascent, right? But then observe, so what you do is you initialize the weights. You have, this term is easy to compute, but then for the second term, you initialize the weights, you let the network run to obtain simulated state samples, compute gradients, update weights, iterate. Very simple. Now this still looks complex till you realize something very strange. This is exactly what we did for the Hopfield network, right? What we did for the Hopfield network was exactly this. We let the network evolve, we picked up a snapshot. Then we initialize the network and let the network evolve, we picked up a snapshot. We initialize the network, you let it evolve, you picked up the snapshot. Gathered all of those, and if you let it evolve, the Hopfield network was going to find these valleys. So you pulled down the target patterns, you pulled up the valleys, and this is just the update rule for the Hopfield network. So it turns out that after all that really chunky math, the update rule for the Boltzmann machine is exactly the same as the update rule for the Hopfield network. The only thing that changed was the manner in which the network evolved, which became probabilistic, right? And that's very beautiful. When you go through a lot of math and then you end up with something that's so trivially simple, it's very satisfying. Yes?
So, if a desired point is in the valley, then if we just take the snapshots after it evolves, the snapshots might also consider the desired point, right?
in this coin, that is true. Where the point is, so if you take a sufficient number of snapshots, that guy being in a valley is going to occur much less frequently than the rest of the guys. So you can be more careful by checking that it's not one of the, yeah.
I mean, if we randomly initially one time, then I think there is some bias, even if we run in that time.
So you can keep, so again, these are, you can keep randomly initializing differently each time. Or you can hope that if you get to the end, you just wait long enough, you're going to see the entire space. But you're right. The more appropriate thing to do would be to initialize multiple times, right? But it's just that computationally it's cheaper to just let it evolve, right? But then we're not even done with that, right? Before we get to even all of that, let's tackle the other problem. The entire mechanism only stores n-bit patterns. I want to increase the capacity of the network. So we saw how we can increase the capacity of the network in the last class. I can add a bunch of don't care bits whose value I'm not particularly bothered about. And once I add a bunch of don't care bits, the capacity of the network went up from n to n plus k, right? But then we're only interested in the first 10 patterns. How does it change the learning? We introduced this notation. This we call as visible patterns. These we call the hidden neurons. Now, for a given visible pattern, there are 2 raised to k possible hidden patterns, so we have to worry about these. And which of these must be assigned to a particular visible pattern? Ideally, you should assign the hidden pattern that has the lowest energy to make the visible pattern much more memorable, right? Lowest energy for that particular visible pattern. But that's an exponential search space. So instead, skipping that, we're going to make the whole thing probabilistic. So here was the Boltzmann machine without hidden units, right? With hidden units, now the problem with if you have the hidden units, the complete pattern, even for the training patterns, is unknown. There's a visible set and there's a hidden set. So what happens? I can represent the bit pattern as a combination of two sub-patterns, the visible bits and the hidden bits. The energy itself is defined over the entire pattern. So if I want to compute the probability of a visible bit, I have to marginalize over all the hidden patterns, right? Which means that if I want to train this network using the stochastic framework, I want to maximize the probability of the desired patterns of visible bits because I don't really care about the hidden bits, which means that this term is what I must be maximizing, but the probability that I can actually compute for the network is this guy, right? So here's how I do it. The probability of the visible bits is going to be the sum of the probabilities of the full state over all possible hidden patterns. That's all I've done. The thing that I've taken is to compute the probability of the visible bits I've summed over all hidden patterns, okay? So if I take the log probability of one hidden visible pattern now ends up with 2 of these guys, where within each of these guys I get this ugly summation over an exponential number of terms, right? If I take the derivative and work through the arithmetic without actually torturing you with it, what it ends up being is that the derivative now has 2 components. For the first component, I'm going to be taking the average over all of the visible patterns that I want to store, but inside it, I'm getting a weighted combination of pairs of bits, where the weighted combination that is taken, where the weights are obtained from the conditional probability of the states given that the visible patterns are fixed. That's for the first guy. For the second guy, I'm getting the denominator really didn't change, right? Now once again, this is an expectation, right? This is an expectation, conditional expectation, because the v is fixed, you just have to sum over h. Conditional expectations, again we saw, even if you have to sum over exponential terms, the shortcut is to just run this through simulation and sampling. So that means that what you can do is, when you actually add the hidden bits to your network, now you have to do sampling twice. First, to compute this term, you're going to have to run many simulations where you fix the visible bits and let only the hidden bits evolve, and now you take the product of pairs of bits. And to compute this term, you let the entire network evolve and take the product of pairs of bits. Now this looks kind of complex, but in practice it's going to be very simple. So again, we're just going to be doing more simulations. So here's what we would do. For each training pattern, you fix these guys, you let the network evolve. And when it evolves at steady state, you're going to get some pattern over these hidden bits. You take a snapshot. So you attach the visible bits and this hidden snapshot. You call it one training sample. Repeat the process many, many times. For each training sample, you repeat the process many times. And now each training sample becomes a large number of extended patterns, where in each extended pattern, the only thing that changed was the hidden bits. Right? So this you're going to use as your new training set, which is now the visible bits augmented with the generated hidden bits. And the rest of the training is exactly the same as before. For the rest of the bits, for the second term, you just let the entire, you don't fix the hidden patterns, right? Visible patterns. You let the entire network evolve. You unclamp the visible bits and let the entire network evolve several times to generate a bunch of simulated samples. And now your gradients are computed exactly the same as before. The only thing that happened is that this first term is now averaged over n times k patterns, because each of your n training patterns got expanded into n times k extended patterns because you drew a k samples of the hidden patterns, right? So the fun stuff is that the math seems to get increasingly complicated, but then when you get down to brass tacks, it's really nothing complex. It's very simple. It's very beautiful. Questions? Yeah.
In this model, do we still train over the hidden weights? Do we still train on the hidden weights?
Yeah, all of them, right? The hidden weights are also being trained. The entire network is being trained.
But then, what is the difference between using a hidden neurons instead of just train a n plus k Boltzmann machine?
That's exactly what you're doing, except that for the training instances, you're only providing the n bits. You're only providing the visible bits. You don't know what the hidden bits are, right? So this is exactly the same as training an n plus k Boltzmann machine, except that because for the visible bits, for the patterns, only the visible bits are provided. You ran a first bunch of simulations to generate the hidden bits, and you extended your training bits. So this is exactly what you're doing, what you suggested, right? It's about how you generate your training data, right? So it's kind of cute, very cute. So the overall training process is just this. You initialize your weights. You run simulations to get where you first clamp the visible bits and generate many instances of the hidden bits. Then you unclamp the visible bits so that the entire network evolves. You get a second set of simulated samples. Plug those into this formula to compute gradients. You perform gradient ascent, right? So these Boltzmann machines are kind of cute. The stochastic extensions of Hopfield networks, they enable storage of many more patterns in Hopfield networks, but also enable computation of probabilities of patterns, completion of patterns, and so on. The problem is, so here's the overall process, and this is the process for the evolution of the network. This is the process for training the network. So there are two sides to this figure. The left shows you how the network evolves. The right shows you how the parameters are trained. Okay. Now, if you want to run pattern completion, let's say I have a part of Bugs Bunny and I want to finish the rest of it, fix the rest, estimate the rest of it. These are the bits of Bugs Bunny that I know. I fix those. Then I let the network evolve where it learns all of these guys, but also these guys, and let it run many, many times till steady state. And then finally, I take many snapshots and then just take the average value of these bits. They take the signs of the average value of these bits. I get back my memory, right? Or if I'm doing denoising, it's going to be pretty much the same thing, right? Same process, except here you wouldn't be holding anything fixed. You just let the entire network evolve. But you'd only be taking the average of the visible bits. And you wouldn't actually get something like this. In this case, you'd actually get something much cleaner. So, but you can use this for classification. How can I use this for classification? This is very interesting. So if you think of classification, that's really just a pattern completion problem. I don't think you've ever thought of classification as pattern completion. But classification is pattern completion. Why is classification pattern completion? Here's how my training data looks like. My training data is going to be F1, F2, F3. I'm assuming right now that all of my features are binary. I've binarized my features. But I can also, if they're real valued, there are extensions to the model which will deal with it. F4. And then I have a class. Let's say I have 10 classes. I can represent my 10 classes as a one-hot vector, right? I don't even have to represent it as a one-hot vector. I can represent the class IDs as a 4-bit sequence. But let's say I represent it as a one-hot vector. Then there's going to be C1 through C10. This is going to be my visible pattern. I train my network using these visible patterns. Later on, when I want to perform classification, what has happened? These bits are not seen. These bits are not seen, right? I run pattern classification, voila. I'm going to get my classification output. So this actually can perform classification. Problem is that there can be any number of patterns, and even for a single training instance, you have to run so many simulations just to extend the training pattern to get all the hidden bits. So training takes forever and doesn't really work for very large problems, but then it turns out you can actually simplify things greatly by doing something called restricted Boltzmann machines, which is what anybody uses. Now in your standard Boltzmann machine, the network was complete, which meant that every training bit spoke to every other every visible bit spoke to every other visible bit, every hidden bit spoke to every other hidden bit. I'm going to make it a bipartite graph. I'm going to say the visible bits don't talk to one another. Visible bits only talk to hidden bits. Hidden bits only talk to visible bits, right? I've sort of partitioned the graph. This is very simple. And this was originally proposed as the harmonium model by Paul Smolensky, but then the first people who really made this famous were Terry Sejnowski and Jeff Hinton. So now I can still use exactly the same behavior as before for evolution. Now for any of these guys, let's say I give you a bunch of visible bits, or give you a bunch of bits in this layer. To find out what I should set this bit to, I just compute the standard logistic using these guys and flip a coin. I don't have to consider these fellows because hidden bits only see visible bits and vice versa, right? So the entire evolution is going to look like this. For the hidden bits, you're going to get a weighted for each bit, you're going to get a weighted combination of the visible bits, compute a logistic, and use that to decide whether the bit must be a 1 or a 0. For visible bits, you're going to compute a weighted combination of the hidden bits and use that to decide whether the bit must be a 1 or a 0. What would the storage capacity of this guy be? It's still going to be n plus k, more or less, right? So so if I want to remember, how would you train it? Remember in the when you were training a full Boltzmann machine, everything was connected. So you would fix the visible bits, let these guys evolve, generate extended training patterns, and then use those for your training setup. Here, something interesting happens. Here, finding these fellows required a lot of iteration because each bit, hidden bit, influenced every other hidden bit. That is no longer going to be required over here. Hidden bits only talk to visible bits, right? So which means there's no iteration, there's a single snapshot. I give you the visible bits, I compute the hidden bits in one snapshot, I'm done, right? The second step when you are training the Boltzmann machine is that you freed these guys up and you let the entire network evolve to generate a bunch of samples. In this case, it's going to be somewhat simpler. You would free up these bits, you initialize these guys, you can use these to set these patterns, set these bits. Then using those bits, you can go back and set these bits. Using these bits, you can go back and set these bits just by using the standard sampling mechanism to update the bits, right? And so if I were to plot the whole thing, what I would do is I would set the initial visible bits, from those I get the hidden bits, then from those I get the visible bits, and so on. And then when I want to compute the contribution of any particular pattern that I'm trying to store to the overall gradient, all I need to do is to compute the product of these two guys for the first term in my gradient, and the product of these same two guys after the network is fully evolved for the second time in my gradient. So observe that this is going to capture the valley just downstream of the pattern that you're trying to store, right? Same. So it's, and because the weights are symmetric, it's kind of you don't have to do very much more than that. But then let's go right back to Hopfield networks. We said that when I'm trying to fix the train the Hopfield network, there's no need for me to start from here, go all the way to the bottom of the valley, and then raise the valley. It was enough for me to take 1 or 2 steps, and then just raise wherever I arrived at, and that should give me a good enough solution, right? That means over here, I can just do something like that, and this product is going to be the first term in my gradient, and this product is going to be the second term in my gradient, just 1 step or 2 steps, and then I can apply the update rule, and the whole thing becomes very simple. Now suddenly you've taken this very complicated machine and converted it into something very tractable indeed, right? So this is your restricted Boltzmann machine. So RBMs again are excellent generative models for binary or binarized data. Again, you're speaking of binary data, but they can also be extended to continuous valued data. There's a nice paper called Exponential Family Harmoniums with an application to information retrieval by Max Welling in 2004. It can be used for classification, as we just saw. Nothing changed, right? This is exactly, RBMs are no different from full Boltzmann machines when it comes to pattern completion, which means it can be used for classification. It can be used for regression. I give you the dependent variable, independent variable, I ask you to predict the dependent variable. I treat the combination of dependent and independent variables as the extended visible pattern, and I train my network. And later, when I'm trying to make a prediction, I just clamp the values of the independent variables. It's going to predict the dependent variable, right? So it can be used for regression. You can use it for continuous valued. You can convert it to make it continuous valued, deal with continuous valued inputs by saying that for the visible units, what you see is just going to be a trigger for a downstream exponential model, which is what this paper was about. And then there are other variants where instead of just having a visible unit talk to the hidden unit and back, you can extend the model to say that the visible units talk to hidden units, which talk to another layer of hidden units, which talk to another layer of hidden units, and the whole process, the machine becomes more complicated and deeper, but the basic ideas really remain the same, because if you think about it, this whole thing can be collapsed into one large network of hidden units, and they are talking to one layer of visible units, right? And you can also make it so that these edges are no longer symmetric. And all of this is simply a basic extension of whatever we saw so far. And I've gone through a whole bunch. I've talked about, but I've also missed a lot of topics like algorithms for learning and inference, or RBMs, mean field approximations, using RBMs as feature extractors, as generative models, more structured DBMs. But all of those you should be able to understand fairly easily by going over the literature. But what I have done over here is to spend a lot of effort. In fact, I spend what most people would consider an unnecessary amount of time on Hopfield networks, because at least from where I stand, the way I see it, the maths of Hopfield networks is very simple. It's just, if you're just dealing with quadratics and optimizing quadratics, the whole thing was very easy to understand. But by going from Hopfield networks to the Boltzmann machine, made the whole thing intuitively much clearer as well. If I just present the Boltzmann machine de novo from the beginning as a generative model, at least to a person like me, it seems a little bit of magic. Where did it come from? And seeing the entire story build up gives you a perspective and insight, which allows you to deal with it much more intuitively, right? Anyway, I'll stop over here. If you want to learn more about these things, you can actually read up the literature, and hopefully you have enough of a background to begin to make sense of it. Right? Questions? Thank you.